This problem demands that we do calculus in order to find the electric field at point O. We know that this arc has a fixed radius of r and total charge of plus q is distributed throughout the whole arc. What we need to do is think of the arc as a collection of infinitely small amounts of charge, dq. Each dq contributes to the total q, and each dq is spread around the arc. Now, each dq is going to contribute and make its own dE. And dE is going to just be good old Coulomb's law, but instead of q, we can use dq. And of course, we divide by r squared. Okay, so we're getting pretty close here. We're looking at using Coulomb's law. But as we move across, this arrow is going to start pointing in different directions. You can see the net result should be pointing straight up. Okay, we want to look at some symmetry of this problem though. If we have a dq on this left side at such position, we're going to have another dq on the right side. And that's going to create an electric field that goes like that. Now these are going to have components, component to the left, to the right. They cancel out. So there's some nice symmetry here. A little bit of symmetry to the problem is going to make it a bit easier. Then we have an upward component and an upward component. So we need to double those. We need to double. Assuming we only look at one side, we can simply take the upward component and double it. So we might look at that as our angle. It's going to be reflected over here. Okay. So what is our total electric field? What's that going to look like? Okay, here we go. The total electric field is really the integral of all the infinitely small electric fields, dE's, as we sweep around different thetas. So actually our limits of integration deal with theta starting at 0 and going up to 90. Remember, we're only going to have to do half of this arc. But because we're looking at half, we do need to double. And then I'll get the component in a second. We're going to take 2 times dE, which is k dq over r squared. Right? That's the dE right there. And then we multiply it by the cosine of theta so that we get that upward component. So we're all set. This is looking pretty good. The problem right here, though, is we got to do this. We must replace dq with d theta. Because our variable is theta, our limits of integration are theta, that means the little d quantity has to also be theta. Okay, how can we do this? Here's the trick. Here's what we're going to look at. There's a quantity called linear charge density. And that is important here. The linear charge density is fixed, is constant throughout this entire arc. Now, sometimes we use the symbol lambda for linear charge density. On this problem, you don't really have to introduce lambda because we're going to look at it as a ratio. Total charge divided by actual total distance, right? Half of a circumference, pi r. That's got to equal the infinitely small amount of charge over an infinitely small distance, ds. This little dq is spread out over ds. ds, s. Sometimes we use s as an arc length. Okay? So if we have a little d theta in there, and it's multiplied by r, right? This arc length ds is also equal to r d theta. And we can make that substitution right there. Okay, so when we solve for dq, we need to solve for dq because we're going to substitute it into here. dq, we can cancel that once we substitute in, is going to equal q times d theta over pi. Right, make that substitution. Arc length is radius times arc, angle. Always going to be true, whether it's a big angle or an infinitely small angle. And And then this equation comes about right here because that charge is distributed evenly. Density, the idea of density is important. Okay, so let's write out our final integral and solve it. Here we go. Okay. So our capital E is equal to the integral from theta equals 0 up to 90 to k. Instead of dq, we're going to write capital Q d theta all over pi and r. And then out here we still have cosine theta. So it looks intimidating, doesn't it? It looks like a lot of scary stuff. But all this stuff right here, no biggie. Constant. And whenever you do the integral of constant, all that stuff just comes right outside. And what's the integral we really need to do? It's just cosine of theta, d theta. Anyone can do cosine of theta. That's sine. So our electric field is all this constant, 2k big Q pi r and now we evaluate sine of theta at 0 and 90. When we evaluate at 90, sine of 90 is 1. So we have 2k q over pi r. When we evaluate at 0, sine of 0 is 0. So this quantity is equal to the electric field. It's a vector. I would argue it points upward. Very common problem. Sometimes you'll see not a full half circle. You'll see some different fraction, okay? But you'll always have that symmetry. And you always want to think about the charge density. See if that can help you. There you go.